Welcome to this video on completing the square. First, what is a square? Well, of course we mean in the algebraic sense. In algebra, a square is essentially anything squared. But in this video, we're interested particularly in binomials squared, as you see here. Let's work out the algebra here. Remember that exponents don't distribute into parentheses. And therefore, to square this, we would have to multiply it by itself. This would require a process called FOIL, which would ultimately lead to this. Pause the video if FOIL is unfamiliar to you. Now, we're used to thinking of this as an algebra problem, and this as an answer. At least in the very beginning of algebra, that's the way it's portrayed. When we get a little further in algebra, we sometimes think of the bottom line here as the problem, and we're told to factor, in which case we see the top line as the answer. But in this video, it's important for us not to think of either of these two expressions as a problem or answer, but rather as two equivalent expressions. What do I mean by equivalent? Equivalent expressions are two algebra expressions which always have the same value, regardless of what number you plug into variables for both. If that seems abstract, here's what I mean. Suppose I were to take a random number for x, say 4. And for all of the x's in these two expressions, suppose I plugged in 4. If I followed the order of operations and evaluated all the expressions here, it turns out I'd get the same result for both of these. I'm not suggesting that 4 is relevant particularly to this problem, nor that 81 has anything to do with it, other than the fact that these expressions are equivalent has the meaning that whatever value for x we would plug into them, we would always get the same answer, not just in the particular case of x equals 4. So again, we want to enter this video with the notion that these aren't problems and answers. These are two expressions that always have the same value, no matter what x is. The bottom one we call standard form, and the top one we call a completed square. The one in standard form, because it has three terms in this case, may be called a perfect square trinomial or a square trinomial, sometimes even a perfect square or just a square, many names to refer to that kind of trinomial. Not all trinomials are perfect squares, this one happens to be. So, what is completing the square? Well, it's the title of this video, of course, but what does that mean? To illustrate what it means, I'd like to work out this basic algebra problem first. Suppose in a basic algebra course you were told to simplify this expression. Well, we would have to do the exponents first, which would mean we would have to do FOIL. And after combining like terms from FOIL, we could distribute the 3 and again combine like terms. If you're unfamiliar with this kind of algebra or haven't seen it in a while, hit pause and analyze the particulars. This is not what we'll be doing in this video, but it's important for us to look at the basic algebra to understand what completing the square means. First, notice that this completed square or original problem here, and this is the standard form sort of answer to this problem, and notice that the formats of these two are as shown on the right here, where A, B, C, H, and K represent numbers. Those aren't math problems we're working out. I'm just pointing out the format of the top and bottom line of this chain of algebra. Now, there are going to be times in this video, of course, but also beyond and in other parts of mathematics, where we have to do the reverse of what we just saw. In other words, we have to take a polynomial in standard form and reverse the process and get ourselves back to the completed square form. This is precisely the opposite of what you just witnessed when we were entertaining the notion of being in a basic algebra class. So what this video is, I haven't showed you yet, but what this video is a means by which you can go from standard form to a completed square form, and that is called the process of completing the square. And that's what we're going to learn now. Why would we bother though? What's the point? Well, one thing is that it can help us out in graphing. Here's an example. If I wanted to graph this equation, but I could complete the square on that equation, it would be a lot easier to graph. We'll say more about that later in the video. If you don't see it right now, it's not a big deal. Another reason for completing the square is for solving purposes. If I wanted to solve this equation, and I were able to complete the square on it, then it would be a much easier equation to solve, and we'll say more about that later in the video. But I thought it would be a good time to mention what this all ultimately leads to. Before we get to the three problems we're going to do today, I have to discuss monic versus non-monic trinomials. Here's three trinomials. Monic, by the way, means having a lead coefficient of 1. Let me explain. These two trinomials are monic, their lead coefficient is 1. This trinomial is non-monic. Its lead coefficient is -2. Looking up at the monic trinomials, you'll notice the so-called invisible 1 that often accompanies the x squared when no coefficient is listed. That's just a fundamental consequence of the fourth grade fact that 1 times anything is itself. And so now that we know the difference between monic and non-monic, it's relevant for this video because when you have a monic trinomial, such as the top two, you're going to be able to convert it into a completed square format as shown on the right. By contrast, when you have a non-monic trinomial, such as the last one, you're going to have to convert it into a slightly different format. Now these two formats may look the same, but notice the non-monic completed square conversion format has a coefficient outside of the parentheses, and we typically call that a. So with no further ado, let's actually get into the mathematics and work these three problems. So here's our first of three examples. In this problem, before we start the completing the square process, it may be worth noting that this particular trinomial is factorable. And there are instances in which you want the factored form of a trinomial. There's nothing mathematically wrong with factoring the trinomial, but it doesn't get us any closer to achieving our goal of the completed square format that we're after here. Again, in some circumstances, factoring is very useful. It isn't in this particular case based on our goals. So what do we do then to complete the square here? Well, strangely, if we're going to go from standard form to completed square form, one of the things we want to start with is something we learned in kindergarten. Sounds silly to say, but what is this kindergarten fact that we're going to exploit in this video? In kindergarten, we know that any number plus 0 is itself. And therefore, we can add 0 to anything and not change its mathematical value. So what I'm going to do is take this trinomial here, and I'm going to add a 0 to it. This may seem strange, but watch a very helpful thing that I can do by adding 0. I'm going to take that 0 and replace it with something that equals 0. I think everyone can agree that 9 minus 9 is 0. So I'm going to replace that 0 with 9 minus 9. This may seem like a very strange thing to do. Bear with me. I will later tell you why I chose to do that. But what I want you to see first is not why I chose 9 minus 9, but what happens as a result of me having chosen 9 minus 9. By choosing that form of 0, what I can do is take the first three terms of this expression now and factor them. Watch as I factor the first three terms of this expression. These three terms factor into x plus 3 times x plus 3, which happens to be a factor times itself. And anything times itself can be expressed as a square. I can now replace the first three terms of this expression in green
with x plus 3 quantity squared. And now that I've done that, I can combine the terms outside of the parentheses, and I now have completed square format. But this concept of adding 0 raises an interesting question. Let's go back and look at our 0 again. Could I have, for example, replaced 0 with 5 minus 5? I think we all can agree that 5 minus 5 is 0. And this is a perfectly legal mathematical move, but worth exploring what would have happened if instead of 9 minus 9, I had chosen 5 minus 5, for example. Now, while this is mathematically valid, let's follow the consequence of such a choice. Taking the first three terms and factoring them would have led me to an equivalent mathematical expression. The problem here, though, and there's nothing wrong with what I've done. I could combine my terms on the right. All of these mathematical expressions are equal. I've made no math mistakes whatsoever. But the expression at the bottom of the screen, while equal to the one at the top and mathematically valid, doesn't achieve my goal of completing the square. So while there's nothing wrong with replacing 0 with 5 minus 5, mathematically, it may be particularly unuseful in that it doesn't get us to the place that we want to go. So let's look back at how we had done this problem by replacing 0 with 9 minus 9. But of course, if you're a student in one of my classes, this raises an interesting question. How would you know to replace 0 with 9 minus 9? What we saw was that 9 minus 9 was a good choice, and for example, 5 minus 5 was a bad choice. So here's a thought that we could use to help us decide what to replace our 0 with. The relationship is that you see here between the arrow governed by the 6x. The 6x is called the linear term, and the 6 is called the linear coefficient. And in choosing a replacement for your 0, here's a rule I recommend following. Take the linear coefficient, divide by 2, and square that result. In this particular case, 6 divided by 2 is 3. 3 squared is 9. So by letting the linear coefficient determine my replacement for 0, I'm guaranteed to have success in the completing of the square process. Again, when deciding how to choose your 0, in this case we chose 9 minus 9, take half of the linear coefficient and square it, and you'll know how to create your 0. By the way, it's worth noting here before we go any further that this trick only works for monic trinomials. More later on what to do if your trinomial is not monic. And here's the original presentation that we saw earlier. Let's take a look at another example. Here we have a polynomial in standard form, and our goal is to convert it into a completed square format. So once again, we want to be clever and add 0 in just the right way. First of all, adding 0 is allowed. As we know from kindergarten, adding 0 doesn't change the mathematical value of anything. But the real question is, what do I want to replace my 0 with? Well, in this particular problem, I chose 25 fourths minus 25 fourths. And while that may seem like a strange choice, and I will explain it in a moment, I think we can all agree that 25 fourths minus 25 fourths is definitely 0, and therefore I've made a valid mathematical move here. But valid isn't the only concern. The real concern is it helpful? Well, let me tell you why it will be and how it is that I arrived at 25/4. It's the same rule I used a moment ago. I used the linear coefficient of -5 to determine how I would create my zero. And I used the same rule that we talked about briefly a few moments ago. I took the number -5, divided it by 2, which gives me -5/2, and I squared that, which gave me +25/4. So we're using the same logic here to create our zero. The only difference here is that we get an ugly fraction. Well, that happens sometimes. Nothing we can do to avoid that. But now that and again, it's worth noting that this trick, the divide by 2 and square trick, only works for monic trinomials, which we have here. So what I can do now is take the first 3 terms of that expression, let me set them aside on the right here, and factor them. Now for many students, this looks like a very difficult thing to factor, and I won't disagree with that. But it does in fact factor into what you see here. A shortcut that you'll sort of pick up over time with practice is that the number on the right half of each factor is literally half of the linear term of the original problem. In other words, it's the number you had while using the shortcut before you squared it. But I'll leave that for you to sort out. This, however, is the factorization here. And it does lead to a perfect square trinomial, or a binomial squared, which is equivalent to a perfect square trinomial. And I can now replace the first 3 terms of the original, or not the original, but of the expression on the left with my now completed square. The only remaining thing to do is to combine the terms, the like terms, outside of the parentheses. I'll show you how that works here, but this really is no more than just 5th grade arithmetic. So I took the 2 and replaced it with 8/4, my goal being, of course, a common denominator. And now that I have a common denominator, I combine my numerators. I don't want to turn this into a fraction lesson, so I won't talk more about that, but that is indeed what those terms combine to make. And I've now completed the square on my original standard form polynomial. What does this mean? Well, it doesn't mean that we have any different of an expression. The expression on the bottom of the screen is mathematically equivalent to the expression on the top. If we were to work out or expand out and combine terms, the expression on the bottom, we would in fact get the expression on the top. All we really have when we complete the square is a different format for our polynomial. Why would we want this different format? More on that later. Here's our last example, and it's worth noting here that we do have a polynomial in standard form, but it is not a monic polynomial. Notice the -2 in the front as the lead coefficient. So now the question becomes, unlike the last 2 examples, what do we do when we have a non-monic trinomial? What I like to do, and there are other ways, but this is just my preference, I like to factor that coefficient out of the first 2 terms. Let's take a look at the first 2 terms here, ignoring the -14. What I like to do is factor that -2 out of the first 2 terms of the polynomial. Now it raises an interesting question. Could I, if I wanted to, look at the right side of your screen, could I, if I wanted to, factor a -2 out of the entire thing? Absolutely. There's nothing wrong with doing it that way either. But what you'll see as we proceed is that it's really the first 2 terms that we care about, and that we can sort of set the -14 aside just for algebraic simplicity. If instead you used what you see on the right side of the screen, you would still get the correct answer. It would just be a little bit more algebraically cumbersome. So now that I've factored the lead coefficient out of the first two terms, that leaves me with a monic binomial inside of the parentheses. You see it in blue there more than likely. And what I can do now is, ignoring the rest of the problem, just complete the square on that, on what is inside of the parentheses. So I will ignore everything outside the parentheses and use the same tricks we saw in the last two problems. First, I'll start by adding 0. Then I want to change that 0 into something like 7 minus 7, or 9 minus 9, or 13 minus 13, or whatever is suitable to this problem. And again, what determines suitability here is the linear coefficient. You see the -6 there. Let's use that linear coefficient to complete our square and make a logical choice for what we replace 0 with. Taking the -6, half of that is -3. -3 squared is +9. Therefore, just like we saw two problems ago, I'm going to replace 0 with 9 minus 9. What I can then do is take the first 3 out of 4 terms in the parentheses, complete the square on those, or factor those really, which makes a completed square. And then I now have this expression. But what about the -2 on the outside and the -14 that we've been ignoring thus far? Well, the only way to get this into the final completed square format is to redistribute the -2 that we factored out in the first place. Redistributing the -2 gives me this. I'll pause while your brain processes. You may notice when I redistributed the -2, it multiplied by the -9 to give me +18. And now I can combine the terms that are outside of the parentheses, and I now have a completed square format.
Let's go back to the earlier question of why do we bother to do this? Well, I'll give you a couple of examples that you may or may not understand based on your prior experiences in math. Essentially, I'm done teaching you how to complete the square. Let's look at a couple of applications. Again, these may or may not make sense to you based on your ability level. One of them, as I mentioned earlier, is the notion of graphing. Suppose I wanted to graph this equation without a calculator. With a calculator, of course, I wouldn't bother to complete the square. But to be able to graph this expression without a calculator can be a little cumbersome and require some moderate amount of work. It's not impossible to graph in this format. There are certainly techniques where you can. But let's entertain this thought. This problem we saw earlier as having that expression on the bottom as its completed square. So my idea is this. If I want to graph the top equation, being that these two expressions are equivalent, I could graph it in completed square form instead. Well, why is that any better? Well, it depends. If you're familiar with a topic called graphing via transformations, by the way, check that out on my channel as well. It's quite a bit of information there. But assuming for the moment that you're familiar with that technique, then this is a very easy graph to do without a calculator. Here's what some of you may know. This is the graph of y equals x squared, your basic parabola. If I want to graph x plus 3 quantity squared minus 1, I simply have to take the basic parabola, shift it left 3 spaces, and down 1, leading me to this graph. If you're not familiar with graphing via transformations, then I probably lost you on that, especially on the part where the plus 3 shifted the graph to the left. But nonetheless, If that's a topic you're familiar with, then you can see the tremendous value in completing the square, especially because it makes graphing so much easier.
Let's look at one more example of why we would want to bother completing the square in the first place. That example comes from solving this particular equation. You may notice that the polynomial on the left of this equation is exactly the one that we completed the square on earlier in this video. You may recall this as the result. So if I were asked to solve this equation on the top, I could simply complete the square and replace the left side of the equation with the completed square format. Now, on first glance, one would wonder, is this a particularly helpful way to solve this equation? It doesn't look on first inspection anyways that this equation is any easier to solve than the one it replaced. But that's in fact not true. There's something about a completed square format that makes a quadratic equation pretty straightforward, as you're about to see. So I'm going to use a trick here called isolating the square. What I'm going to do is subtract 4 from both sides, and then divide by the lead coefficient of -2. Simplifying the right gives me the isolated square on one side of the equation and a number on the other. And that's particularly helpful because I can now use the radical property. If using the radical property cancels the square and gives me plus or minus radical 2 on the right side. And now, in order to solve for x, I can simply add 3 to both sides, and I'm now done. And you can see, if you're familiar with this kind of algebra, the fact that I completed the square on this original trinomial made it a very quick and easy equation to solve, whereas it might not have been in its original form.
And that completes this video on completing the square.